Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video is about position tolerance at M and L modifier. And we explain here virtual condition size, outer boundary, inner boundary, and resultant conditions as well. I prepare here two drawing which one position tolerance is applied with 0.2 geometric tolerance or geometric error, and at M modifier with respect to datum A and B and C, datum A control orientation and datum B and C control the location of the axis of the shaft. Here the same position tolerance applied at L modifier, 0.2 at L modifier with respect to datum A and B and C again. Let's, by constructing a table, I explain the difference between these two modifiers and how it acts on the material. The first table here, I draw it. We start with virtual condition size, actual mating envelope, from MMC size, which is 10.2, other size 10.1, 10, 9.9, 9.8 as LMC size. Then we have a geometric tolerance 0.2 for all. And because it is a modifier sends three messages. First, row number 1 does not apply. No perfect form is required. Even at MMC size, you can have 0.2 error. Error here is actually the center or axis of the shaft is allowed to be off center. How much? Zone size is 0.2. It means 0.1 to the right or 0.1 to the left with respect to the true position of the axis, or top or bottom or in any direction. Okay, then after 10.2, which is a modifier, the second message is that the goal of this design is assembly. This shaft will be assembled with another hub as a mating parts. Then assembly is the goal. And designer is very worried about the maximum size of the shaft plus applicable geometric tolerances. Then, and the third message that it sends, it says that the bonus is permitted. Bonus tolerance, it means that manufacturer, if you produce at 10.2, you have allowed to have 0.2 error. But if you depart from 10.2 MMC size, you can have a bonus here. Then we got bonus tolerance is 0 at MMC and departure from MMC 0.1, 0.2, 0.3, 0.4. And so total geometric tolerance, TGT or TT, they show it 0.2. A summation of geometric tolerance and bonus tolerance is total geometric tolerance, 0.3, 0.4, 0.5, 0.6. Okay, we close the table. It means that if you produce at 9.8, you can have 0.6 position error. Let's consider one by one. First, let's start at MMC 10.2 with 0.2 error. It means that, let's assume that this is the true position. This is the true position. Zone is 0.2. And if you consider This is the size of 10.2. But we know that this size cannot happen because we have error. Assume that center is here. Then shaft will be here. If the center is here, shaft will be here. If the center is here, shaft will be here. And if the center is here, I just draw four possible position. Then we have four circles. You can draw. I didn't draw all complete circle, but I showed the amount that it can be switched. It can be switched here, 0.1. It can be switched here, 0.1. It can be switched here, 0.1. It can be switched down to position of the axis 0.1. Then, if you consider the smallest circle that can circumscribe all these circles, it means the envelope size of the shaft is actually a circle with 10.2 plus 10.2 plus 0.2, 0.1 from other sides. Make it what? Then the original is 10.2, and the smallest circle that can circumscribe all of the circles, encloses all circles, possible circles, because the shaft can actually switch up and down, left and right in any direction, 0.1. Then in both directions it should be 0.2, and it added to 10.2, make it 10.4. That's the virtual conditions. That's the point that designer is worried about that. If it is more than 10.4, because he allows 0.2 error for position tolerance, if it is more than 10.4, it cannot be assembled. Then this is the virtual conditions. That's the limit. That's the outer boundary. The outer boundary here coincides with the virtual conditions size. Okay. What about inner boundary? Inner boundary, assume that we got the shaft at 9.8. At 9.8, let's say true position here. Assume that exact true position of the axis is here. Draw a circle at 9.8. But we know that it cannot be happened. But position here can be 0.3, left, right, up, bottom, down, 0.3, each side 0.3. Each side 0.3. It means that I can draw circles at here. I consider part of the circle. I put axis here, draw the same axis here. I put axis here, center here, draw a circle. I just show a part of the circle which is important. And here, you see I just draw one of them, which is this one. Just one of them. You can draw the rest. Yeah. And there are lots of circles. Inner limit is a circle, the largest circle that can inscribe all these circles. the largest circle that is inside and touch with or in contact, in tangent to all of them, is the inner boundary. Then I put here, from each side, you can come inside 0.3. It means 9.8 LMC minus GT here is equal to 9.8 minus 0.6, 9.2. That's the inner boundary and also is a resultant conditions at this size. The minimum conditions. If I draw this inscribed circle, this one is the inner boundary in this case. And this is the resultant conditions as well. What does it mean? It means manufacture. If you produce at 9.8 and you have 0.6 zone for your position error, it means from each side 0.3. Assume that you switched at 9.8 diameter, your axis is off 0.3 to the left or to the right. We have to remove from one side the material from one side in order to return it back to center. What does it mean? It means that the diameter changes from 9.8 to 9.2. And still is acceptable because we allowed that. We allowed 0.6 position error. And material in this case, which is equal to a shaft with 9.2 diameter, is sufficient to protect the shaft and the part and the application. Then that's for M modifier. Then this is the inner boundary, which is coincident with resultant conditions. Resultant conditions for inner boundary is 9.2. I can add a column here that writes resultant conditions, and for this size is 9.2. It doesn't mean that resultant conditions for other sizes is also 9.2. No, it is after production. You must measure the size, you must measure the error, you subtract from each other and find the resultant conditions for that specific size. But because all of them are larger than this one, here we keep the minimum one and say that, okay, don't go less than this and don't go more than that. Outer boundary, inner boundary, virtual conditions, and resultant conditions. Let's return back to the L modifier. Okay. For L modifier, I construct the table again. Virtual condition, actual mating envelope from MMC 10.2, 10.1, 10, 9.9, 9.8, which is LMC, and geometric tolerance, position geometric tolerance 0.2, 0.2. At LMC, what does mean L modifier here? L modifier here means first, roll number 1 does not apply, is overridden. No perfect form here also is required. Even if you produce at 10.2, you are allowed to have 0.2 error, geometric error. Okay, then second, at LMC, least material condition, you are allowed to have 0.2 error, not more. That's it. It means that, and third message is a bonus is permitted if you depart from LMC size. Then bonus for LMC is 0. For this one, how much you depart? 0.1, how much 0.2, how much 0.3, how much 0.4. That's a bonus. And total geometric tolerance is the summation of bonus and geometric tolerance, 0.6, 0.5, 0.4, 0.3, 0.2. That's the table here. What about, we add this column as well and explain. It means that our goal is not assembly. L modifier means that material sufficiency is the question. Material sufficiency is important for the designer to protect the part and protect the application. And how much is the material inside the boundaries? Then you must take, we are not worried about the larger sizes. We are not worried about the larger sizes. We just worried about LMC size, 9.8. If we produce 9.8, and we have a 0.2 space for our errors, it will be 0.2 zone. Let's I draw. I can remove this table just here. Let's I draw 0.2. This is the true position of the axis, and this is the zone. 0.2 size is 0.2. Each side is 0.1. 0.1 left, 0.1 right, 0.1 top, 0.1 bottom. It can be displaced. Let's draw 9.8 here. The circle. That's the ideal case. But it cannot happen. That's the ideal case that unfortunately you can see this completely. Let's say draw it. Position tolerance, true position, and then 0.2 error, position tolerance 0.2 error. Then assume that we draw a circle that shows that the position of the shaft at 9.8. But we know that this is not true. We cannot produce a shaft exactly at its center. This is why we give permission to the manufacturer that you can have error. How much? 0.1 in each side, in each direction, 0.1. Assume that the axis is here, and the shaft is 9 point. Shaft is 9 point here. Draw it. Moving over here. And just draw part of a circle over here. Then let's say draw it by hand. Then we will see that the largest circle that can inscribe here between all circles. The largest circle that can inscribe here is the inner boundary. Then inner boundary is 9.8 minus 0.2, 9.6. That's the virtual conditions. That's what actually the designer is worried about it. It says that don't go less than 9.6. 9.6 is our inner boundary virtual conditions and consigned with inner boundary, the same as inner boundary. Then what happened? What does it mean? It means that because the goal here is material sufficiency, if you produce shaft at 9.8, but this 9.8 is off center and 0.1 off center, and we wanted to return it back, the diameter actually is 9.8, but this is off center. And we wanted to return the center back. How we can return the center of the shaft back? Just by removing the material from the shaft, from the side that it is shifted. When you remove the material, you make the shaft perfect, but a small thinner. It means the cross section is thinner. You make the shaft narrow. You decrease the diameter of the shaft. How much you are allowed to decrease the diameter of the shaft? How much you are allowed to remove the material from the shaft? This 9.6 is the limit of that. You shouldn't go under 9.6. 9.6 is the limit of this design. This is why it is virtual condition. And designers say to manufacturers, if you made a mistake, you want to correct it by removing the material, for example, then don't go less than 9.6. But what happened? If we produce at 10.2, at 10.2 we can have 0.6 error. What happened? Then inner boundary or virtual conditions here is equal to LMC minus GT is virtual conditions, the same as inner boundary, consigned with inner boundary here, with L modified. What happened? Let's go for outer boundary or resultant conditions. Then, if we produce at 10.2, we are allowed to have 0.6 error. It means 0.3 to the left, 0.3 to the right, 0.3 to the top, 0.3 to the bottom. The axis can shift it. Okay, we wanted this. If you draw a circle, that position tolerance to true center is here, 0.3 here, 0.3 here. If you draw, for example, real 10.6, okay, 10.2, sorry. But if you shift it in this direction, then the axe shaft should be here. If you shift it in this direction, the shaft should be here. And you shift it in this direction, center will be here, shifted here. The shaft will be here. Otherwise, if your center is here, the shaft will be here. I just draw a part of the circles. Then, if you find the smallest circle that actually circumscribe all this circle, encloses all this circle, envelope of all these circles, how much is the size? 10.8. 0.3 from each side. Okay? You wanted to include all conditions. This is your resultant conditions, and the size is 10.2 plus 0.6, 10.8. Then you can write actually outer boundary is MMC plus applicable geometric tolerance. It doesn't matter which geometric tolerance or geometric error made this 0.6. Okay, then it is 10.2 plus 0.6, 10.8. Then you have an outer boundary here, which is RC for size 10.2. It means that for the other sizes, we have RC as well, but this is the maximum one. The others are here, included here, and there is no reason to consider them. We are worried about resultant conditions, maximum resultant conditions, which is 10.8. Here, for size 10.2. This is outer boundary as well. This is the maximum envelope size of this chart. Why we consider here maximum envelope size? What's the application of that? Because the goal is not assembly. Why it matters that the maximum is 10.8? It shouldn't be 10.9 or 11. We don't accept that. Because there are more parts in these machines that are besides this part. If it is 10.8 or more than 10.8, maybe it is in contact with the other parts and take the place of them, or actually engage with the other parts. Then there is a limit for how large it is, and there is a limit how thin it is, how narrow the section, how thin the section is, because the goal here is to protect the part. Does the part have enough material to protect its strength? This is why inner boundary tells us. If you go less than 9.6, the part cannot actually be protected and it will be weaker. The strength here is the most important goal in this design. Then you will see we just compare all conditions, M modifier and L modifier. It can be due to any geometric tolerance that apply to feature of size, not only position tolerance. It can be orientation, it can be a straightness applied to feature of size. The story is the same: inner boundary, outer boundary, resultant conditions, virtual conditions. And the reason is the goal assembly, or the goal is material sufficiency. That's it. Thank you for watching. See you in the next video.